Patterson here. Today we're going to go over atomic theory for physical science. So let's talk about the size of an atom. Atoms are super tiny. You just don't realize how small they are till you put it in a perspective. So let's look at this dot right here, this dot above this eye. That is approximately about 5 million atoms to make up just that one dot. If I write a sentence and I put a little dot at the end of a sentence, make a period, that's about 5 million atoms. So for me to barely be able to see something like that, that's 5 million atoms. So imagine just how small one is. It's very hard to visualize. So we need to go back to the beginning. Where did the idea of atoms come from? So let's talk about Democritus. He was a Greek philosopher, and he believed that the universe had these little pieces inside that were uncuttable, which means I could not break them apart. So there were particles that could not be broken down to pieces that were smaller than what they were. He came up with the idea and how we come up with the word of an atom. So he named it atomos, okay, that means uncuttable, and so that's where we get our word atom. Democritus's theory was one that was kind of simple, and today we look back on it and we think, well, that's kind of obvious, but at this time it wasn't. So he proposed that the shape of an atom determined the properties of that substance, and this is what this means. He said that there were fire atoms, and fire atoms were really jagged, spiky, they were hot, and that's why it hurt to touch something that was hot or on fire. So these atoms were poking into your skin. If you had wine atoms, they were round, they were shiny. This is why wine rolled in an atom or water reflected light. And he saw clay atoms, and these were atoms that stuck together. So if I took bread or dough, or if I took mud, they stick together. And he said these clay atoms have these jagged pieces that would just naturally hook into each other and hold stuff together. This was very rudimentary, but it was kind of an idea that got other people to start thinking about, well, what makes up matter? Next, we have Aristotle. And Aristotle is a famous philosopher, and he lived around the same time as Democritus. So Democritus's theory got him thinking, there's got to be a little bit more to this. So he argued that all matter was made up of 4 elements. And Aristotle's theory was so well received that it lasted for 2,000 years. And when I show you his theory, you're going to probably make some references to certain types of cartoons and stuff. But this theory lasted for 2,000 years, and it was really hard to debunk it. So Aristotle's theory was that you had 4 elements. You had earth, you had fire, you had water, and you had air. So if you've ever played as a kid with Skylanders, you had these elements, and they all had very specific properties. The Last Skybender, you kind of see. So this is something that has been around for a very long time. And we all know water has a lot of different properties than like earth and fire. And so this was very hard to debunk. Next we have John Dalton, and he proposed the theory that all matter is made up of individual particles called atoms which cannot be divided. So he supported Democritus's idea. And he said, hey, I'm going to go a little bit further with this. So this was 1808. And this is kind of real recent when we talk about scientific discoveries. So 1808, Dalton comes along with this theory. And this is where we pretty much stand today. One part of it's a little different, but we pretty much agree with all of this. He said that all matter was made of atoms, and each element was made of atoms. So when I look on the periodic table, sulfur's made of atoms, chlorine are made of atoms, and bromine is made of atoms. He also said that atoms were like solid spheres, like an 8-ball. If you've ever had a billiard ball or a pool ball and you held it, it's really solid, it's kind of heavy, and he predicted that atoms were very dense all the way through like a pool ball. Atoms of different elements differ in mass. So when I look on the periodic table, I can see that. I have potassium, okay, I have this mass, I have tin, I have this mass, I have lithium, I have this mass, and we recognize that yes, they all have different masses. Atoms were indivisible, which means that they cannot be cut, and they were indestructible. I cannot create atoms, I cannot destroy atoms. So we cannot break them down or be destroyed. And that goes back to our conservation of matter. Atoms can combine to form compounds. So I can have oxygen and hydrogen to make water. I can have carbon and oxygen to make carbon dioxide. I can put a bunch of carbons, hydrogens, and oxygens together and make sugar. So I can make these compounds. The only one that we do not agree with right now is number 2. We no longer believe that these are solid spheres. We have a different theory, and we're going to talk through those as we go. But all the other ones, the other 4, we agree with those. So Dalton's atomic model showed that the element was a solid sphere, but with different masses from other pieces. So pretend like this is sodium, this is oxygen. So these would all be round solid spheres, but I would have different masses for those. Next we have J.J. Thompson, and he was the first to discover that atoms were made of even smaller particles called electrons. And he did a very kind of simple experiment. He did what's called the cathode ray experiment. And what this cathode ray does is it sends charges through this tube. I have a gas in here, and it sends electrical charges through this tube. The beam that goes through here, these atoms that get pushed through, all have a negative charge. So if I take a magnet and start putting a magnet towards this little line, what would I predict would happen? So he put the negative part of the magnet up to the line, and it repelled it. It pushed it away. And he thought, that's interesting. So he goes and he turns it around, and the positive side attracted it. So what did he get from this experiment? All right, he recognized that if I take negative and put this and it repels it, this has to be negative. If I turn it around and this positive side attracts it, then this has to be negative too. If this was repelled by the negative and the positive, then there's something else going on. So he recognized that likes repel, opposites attract, and he recognized that this had a negative charge. Okay, so this experiment showed that an atom has a charge, but the scientists were still unclear about how the atom was set up. What's the structure and where is everything in this atom? So he came up with what was called the plum pudding model. And he said that it's kind of like a chocolate chip cookie. It's kind of a really good way to say it. Plum pudding is a dessert that they have in England, and that's what he represented it as. We think of it kind of like in the US, a chocolate chip cookie. This is the cookie part. And negative electrons are the chocolate chip. And the chocolate chip is embedded into that cookie. And that's how he imagined the atom to be. That it's a solid sphere, kind of like a solid cookie. And then the inside embedded into it, the outside of it or into it, were these negative charges. So he called this the plum pudding model. Okay. And then later on we had Ernest Rutherford. He comes along and he discovered that the atom has a positive center. He discovered protons, and it was by accident. He was just kind of checking to see the charge of an atom, and he was able to predict something else. So he did what was called the gold foil experiment. So the gold foil experiment was a really kind of simple experiment also. What he did was he took alpha particles, which are kind of these little pieces that are positively charged, that are going to come flying through a very thin piece of gold. He expected all of this stuff to bounce back out. But what he found was a majority of it went right through. And that really got him thinking, well, why is it going through? And every once in a while, you would have one that bounced out. So what he recognized was that the atom was mostly space, and that these pieces that bounced out actually bounced out because they hit something in the atom that was positive. But a majority of it went through, so that said that there's space in there, like it's allowing it to pass through. So let's say I have a chain link fence. And I give everybody a bucket of frozen peas, and I tell them to throw it at the fence. what's going to happen to these P's? A majority of them are going to be able to go through the fence. So a lot of the P's will just fly through. But there's going to be some that are going to bounce back because they are hitting part of the fence. And this is kind of what happened in Rutherford's experiment. The gold was allowing some of these particles to be bounced back, but there was a lot of space inside that gold foil that allowed the alpha particles to fly through. So a majority went through the holes, okay, and some bounced back out. So this is kind of what Rutherford's gold foil experiment demonstrated. So here's another example if I saw it at like a molecular level. Here is a nucleus of a gold atom, and I'm going to shoot these alpha particles in, but every once in a while one is actually going to hit one of those nuclei and it's going to reflect it and bounce back out. Others are going to fly through, and then I'll have another one that will hit, and it will hit at another angle and it will pop it out the other side. And so that's what he recognized when he did this experiment. So he drew a new model, and it was called a planetary model. And he said, hey, in the middle, I have something positive. And on the outside is where I'm going to have my negative electrons. So the atom is mostly space. And he recognized it because it was kind of like the sun and our planets going around in an orbit. So today when we see an atom, if you've ever seen Big Bang Theory on TV, they have an atom like this, and this is a Rutherford's atomic model. We don't really agree with how the electrons are in this model, but it's a good representation of electrons are on the outside. Protons, a positive nucleus, is on the inside. And so he was able to identify the positive center. Next we have Chadwick. He actually studied under Rutherford, and he discovered the neutral particles inside this nucleus. He recognized that the mass was a little off. If I had all these numbers of protons and they were all the same number, my number should be very specific. But what he recognized was that wasn't the case. Like what he would predict a mass to be was not the mass. And he recognized that there was something in there that was neutral. The center was positive. So nucleus has a positive charge because of the positive protons. But there had to be something else that was in there, but it was not giving off a charge. It was a neutral charge. So he recognized that there's neutrons in there. The neutron mass is just a little different than a proton mass. And now he was able to determine that the center of the atom is still positively charged, but I have protons and neutrons in that center. Niels Bohr comes along and he decides, hey, we need to talk about the electrons and how these orbit around this nucleus. So he put electrons into levels or orbits, and he liked the idea of that planetary model of Rutherford's. And so he said that there are different levels that electrons like to be at and different charges for these electrons. If you want to go over Bohr models, I have a link down in the description where I can show you how to draw out his Bohr models. So he came up with the idea that this first ring can only hold 2, second ring holds 8, third ring holds 18, fourth ring holds 32, and there's other numbers for those other rings. And he said, all right, I cannot have any more electrons in this first ring but 2. If I have more than that, it needs to go to the next level. And so he was able to say, hey, this is kind of how electrons are leveled in an atom. Today, we do not really follow this. It's a really good, simple way just to show the diagram of an atom, but we believe a different electron configuration route today. Now we have Heisenberg. Heisenberg comes up with what's called an uncertainty principle. And you can either know the velocity of an electron or an electron's momentum, but you cannot know both at the same time. So what he is saying is that I can say, hey, I have an electron here and I have a nucleus. I cannot predict both the velocity and the momentum of this electron. So if I asked you guys, all right, I want you to point to your screen, where do you think this next electron is going to be? All right, did you point down here? Probably not. All right, if I said, all right, do it again, And if I did it again, all of these are places that this electron could be here, but it could be anywhere within this black space. But I can't predict both of them. I can tell you how fast it's going, or I can tell you just its momentum, but I cannot tell you both. So it's an uncertainty. We are uncertain where exactly these electrons are at one given time. So today we go with kind of what's called an atomic cloud model, and this kind of goes with Heisenberg's uncertainty principle. I know if I have an atom that electrons are going to be, the probability of finding them here are going to be a lot higher than out here on this far out ring. So I can say with more certainty that electrons are here. The more electrons I have, the denser this cloud around the nucleus will be because I will have more electrons, and I can predict with more certainty that these electrons are going to be here. The further I get out, the less certain I am, but there is a possibility that electrons can be out there. So we know they're here, but we cannot say for certain exactly kind of where they're at one specific moment in time. So we kind of go more with this cloud model. When you guys get more into chemistry, they'll start talking about P levels and S levels, and that kind of goes more into our current theory of what we believe electron configuration is. All right, this was your overview for atomic theory. This is kind of how we started out and where we're at now. I hope that was helpful. If so, let me know. We'll talk to you guys later.